Elementary Algebra Final Assessment 2 Review Questions 14 through 16 Outcome 4 Applications. Question 14 reads as, at the end of the day, a storekeeper had $1,050 in the cash register, counting both the sale of goods and the sales of tax of 5%. Find the amount that is the tax, round to the nearest dollar if necessary. So let's identify our two parts here. We're looking at the sales of goods. Let's go ahead and assign this a variable. Let's say that the sales of goods is represented by the letter G. The second part that we're looking at is the sales tax. Let's say that the tax is represented by the letter T. Now that we've assigned variables, let's go ahead and look at rewriting or creating a formula to plug this information in. Let's scroll down a bit to give us a little more space. In looking at the sheet that should be in front of you or the review, you can look back and see that what we're going to do is add together the goods plus the tax. We know that the goods plus the tax equals what was in the register at the end of the day, which was $1,050. There's our first problem or formula. Next, we want to look at tax. We know that tax, from experience, is going to be the amount of the goods times the sales tax. In this case, the sales tax is 5%. Before we can plug it into the formula, we need to put it into a decimal form. So 5 cents becomes a 0.05 times the amount of goods. Now let's take these two formulas and combine them to create a formula in a single variable. We'll take the second formula and plug it into the first. So we're going to take that first formula where we have the goods plus the tax. Well, we know that the tax is going to be equal to 0.05 G. So we'll plug that into the T's position equals $1,050. Now we can go ahead and solve for G. We combine the G, or 1G, plus the 0.05. This results in 1.05 G is equal to 1,050. Next, we're going to go ahead and divide out that 1.05 so that we get the variable G alone. So 1.05 divided in, we find that the goods comes out to 1,000. We have one part of the problem, but what we want to find is the amount of the sales tax. So we need to go back to our original formulas where we had T equal to 0.05 G. We can plug that G that we just found into that position and multiply it out to find the sales tax. So tax is equal to 0.05 times 1,000. So we multiply that, our tax comes out to 50. So we know that our tax was $50. Don't forget to use the dollar sign to indicate that this 50 is dollars. It's part of the final answer. In question number 15, we're told that we have two cars that leave a parking lot and travel in opposite directions. One travels at 10 miles per hour and the other travels at 5 miles per hour. In how many hours will the two cars be 60 miles apart? So let's pull this information out. We know that car 1 and for the moment I'm going to call car 1A, is traveling at a rate of 10 miles per hour. Car 2, which for the moment I'll refer to as B, is traveling at 5 miles per hour. When we look at the two cars, we're being asked that when their two distances are summed together, it equals 60 miles. Well, we also know that the formula for distance is calculated as rate times time. So that means that car 1 its distance will be calculated by its rate of 10 miles per hour times some time, t, that's unknown at this time. Then car 2 or car B, its distance is going to be 5 miles times t. Well, let's look at the equation to find something that we can plug this information into. We know that when we add the distances for car 1 and car 2, they should come out to 60 miles. So our car 1, which we called A, plus the distance for our car 2, which we call B, should be 60 miles. So now let's go back and plug the distances that we know from above into the positions. So car A is at 10t, car B 5t, and carry down that equals 60. Let's continue to solve. We're going to first simplify the problem by combining the like terms. We have a 10t plus a 5t to make a 15t equals 60. Now we can go back and we can divide out that 15 off both sides so that we end up with the variable t alone, and we find that t is equal to 4. T is a time, and if we look back, our times were calculated in hours, so this should be 4 hours. In question number 16, we're told in the instructions to use a table to solve the problem. Let's read the problem. Number 16 reads, George left his home in Seattle and drove to his parents' home for Thanksgiving. It took him 90 minutes to get out of the city due to heavy traffic. Once he got out of the city, he was able to increase his speed by 54 miles per hour, and he drove for another 3.5 hours until he reached his parents' house. If the entire trip was 294 miles, how fast did he drive as he was leaving Seattle? All right, so let's start by creating a table. Now, just looking back, if you remember, these tables are each going to have 4 columns and 2 rows. So we want to draw a table starting out here that's going to have 4 columns and 2 rows that we're going to fill in. Our first column is always going to be whatever our category is. In this case, our category is George driving in and outside of Seattle. So I'm going to put up here my category. So I'm looking at, is he in the city or is he out of the city? Now, in the case of these tables, your labels in that first column are going to be specific to you. Use an example or use terms that make sense to you as you read it out of the sentence. So yours might look slightly different than someone else's. Next, we should have a time, a rate. And if you remember from the last problem, rate times time is going to equal a distance. So look back at the problem. we look back at the problem, when he was inside the town, it took him 90 minutes to get out of the city. So that's his time. But his other time is outside the city, and it's measured rather than minutes in hours. So before we plug that into the table, we want both to be in the same units. So 90 minutes would be 1.5 hours, or 1.5 hours. So I'm going to change that 90 minutes to 1.5 hours. When he's out of the city, he's then traveling 3.5 hours. Next, we want to put in a rate. Well, when we look at the problem, if you look back at the problem, once he got out of the city, he was able to increase his speed by 54 miles per hour. What we don't know was what his initial speed was. We don't know how fast he was moving when he was in the city, so we'll put an X. But what we do know is that X, speed that he was traveling, plus 54 miles per hour is what he was traveling at once he left the city. Now the reason for creating these tables is once we've set it up, we have the time times the rate. This gives us our last column, our distance. So we can put these or carry these over, 1.5 times x, 3.5 times x plus 54. Now we need something to plug this distance into. We know by reading the last sentence in the question, if the entire trip was 294 miles, how fast did he drive as he was leaving? Well, we know that his distance in the city plus his distance outside the city is equal to 294 miles. So let's plug that information in. So we know it's 1.5x from our table, plus out of the city, 3.5 times x plus 54 equals 294. Let's continue on and let's simplify this problem to solve for x. We'll start by distributing the 3.5 through the parentheses. So I end up with that 1.5x staying the same. Distribute the 3.5 to the x to get a 3.5x, then distribute it onto the 54 to get 189, and then carry down the 294. Continuing to simplify, let's combine the two like terms, the 1.5 and the 3.5, to get a 5x. Carry down everything else that we have yet to use, so that 189 equals 294. We'll now move the 189 out by subtracting it off both sides. This leaves us with 5x equals our 105. What's happened here in the middle, our 109 minus our 109 has resulted in a 0. Lastly, we want to divide out that 5 so that x is alone. So it clears out the 5's. So we're left with x over here equals 21. Now we want to look back. Kind of peek back at your table. Kind of pop up here. We can see that x is actually the rate. It's the speed that he's moving. So that 21 needs to have the units miles per hour to be complete. So your final answer is that he he was driving while in the city 21 miles per hour.